there's any big stuff right now to start with. Landon?
Can you do 5 on the question?
Review number 5?
Yeah.
Okay. So this is one that you just do on your calculator. So the question probably is, how do I get to the log base? So again, the way we do that is we press the math button. It's here on the left. And you scroll all the way down to the bottom till you find the log base command. So I went up to get to the bottom because it's a little bit faster pressing down a million times, but either is fine. And then you just type it in exactly like it looks. So 3 divided by 2, and then 9 divided by 4, and enter. Anybody else? Yep. So here we're just using our definition of a logarithm that says like b to the a is equal to x if and only if log base b of x is equal to a. So in this case, my b is 3, my a is -4, and my x would be like 1 over 81, right? So I just plug it into this side. So I say log of 3, or log base 3 of 1 over 81 is equal to -4. There's nothing to do after that. You just put it in the things in a different spot.
Okay.
So you're just using that definition to do the rearranging. So it should be real easy, right? Nothing tricky about it. You might have noticed on the answer key, I think I boogered that when I wrote the wrong number there. Let me just fix that real quick. Now it's ready. Anybody else? Emma?
Number 10.
So the expanding problems, the order in which we want to do an expansion is quotient, product, power. So we're looking inside the logarithm to do those properties for an expanding one. So I see no division going on, so there's no quotient. But I do see multiplication going on. In fact, I see 2 multiplication symbols. There's one in between the x and the y, and another one between the y and the z. So there's 2 product properties that I can do. So the product property allows me to break all these things that are multiplied together up, put them in their own separate logarithms, and put a plus sign in between them. Now I'm going to go look for power properties. So I'm going to be looking inside each individual logarithm. And for the power properties, I'm looking for an exponent. So I see an exponent in each of these 3 logarithms, so I can do a power property 3 times. What the power property allows me to do is to move that exponent to a coefficient outside the logarithm. And that's it. Is that okay, Emma?
Mm-hmm.
Landon?
Can you do a condensing version, like 12 volts?
Okay, so let's just do 12, I guess, for the sake of argument. Here, the order is reversed, so we're doing power, product, then quotient. And what we're doing on a condensing is we're looking what's going on outside the logarithm. So for the power property, I'm looking for coefficients. So I see 2 coefficients, so I can do power properties on each of those 2, which allows me to move that exponent or that coefficient to the exponent.
So it's just mathematics.
Exactly. Then I'm going to look for product properties. Here, a product property is indicated by the addition. So that allows me to put those two together inside one logarithm. And the last thing I do is I look for quotients, which is going to be indicated by the subtraction. And that allows me to put that together into one logarithm. And that's it.
Can you repeat the order again? Like just the names of the...
So this was the notes on 5.7. For expanding, we do quotient, product, power. And then for condensing, we do power, product, quotient. So that's all there in the 5.7 notes, those sequences. Jack?
U16. Wait, can I just ask a quick question about
Yeah.
the last one?
Sure.
Where did the 8 go? Like, let's see. Did I just like...
Where did the 8 go? Let's see, I forgot to write it down.
Oh, okay, so it's the same as like the first time.
Yep. Sorry about that.
Oh, yeah.
And you said 16?
Yeah.
Okay. So the idea here when solving either an exponential or a logarithmic equation, the first part is going to be to try to get the exponential or the logarithmic part by itself. So to do that, I'm going to add 15 to both sides and then divide by 3. Is that okay? So I'm going to just do that all in one step, if that's okay with you, Jackie. So 12 plus 15 is 27, and 27 divided by 3 is 9. And then to get rid of the logarithm part, I'm going to use an exponent base. So the exponent base I'm going to use in this case is going to be the one that matches the base on the logarithm. So that's going to be 5. So the left-hand side of my equation is the exponent, the right-hand side of the equation is the exponent. The goal, or the advantage there, is that the exponent base 5 cancels the log base 5. And then this is just some god-awful decimal. Or, well, it's not a decimal, it's an integer, but it's a long number. There it is. So then I'm just going to add the 8 to it and divide by the 3. Just like I would do to normal solving. So I get that 65, 0, or 104433. 65, 1044. Something like that. Is that okay? I guess it asked me to round to 3 decimal places in this direction set. Cool. What? Well, apparently having a dump day. Oh, I know what happened. Let's do this. No, I don't know what happened. What did I divide by? Did I do something wrong when I was doing a problem, or when I was... Well, this part is the same. I added 8 to it, divided by 3. That's just, I don't know. Altogether, that's just the wrong number, apparently. I don't have any excuses.
Can you go to the calculator for again?
The calculator
Like-
part.
Like what we do, like what we plug into the pipe.
Well, I just turned 5 to the 9th into a decimal,
Yeah.
right? So that's that. And then I added 8 over and divided by 3.
Or that's it.
The numbers were big, so I just didn't want to do it by hand.
Oh, yeah.
You know what I mean? I didn't do anything fancy. I just did basic, you know,
Oh, yeah.
basic scientific calculator operation stuff. I didn't do, nothing tricky. Cool. Landon?
You do 9.
Okay. So I used, because this is a scientific situation, like we talked about radioactive decay being one of those situations where you use that continuous model, the one with the E in it. So that I used that A equals PERT. So the P is the initial amount. So we had 50 grams of the stuff. So that's where the 50 comes from. It's a half-life, and it's decay. So the half is the 0.5, and the decay is why it's negative. The thing we have to be careful about is that you're losing half the stuff, but not every year, rather every 800 years. So the T there in this problem has to match the rate. So the T there is in number of half-lives. So like every 800 years we're at 25, and then 800 more years we'd at 12 and a half. And 800 more years we'd be at whatever, 6 1/4, and so on. So when I'm putting in my T, I want to convert it into half-lives. So I took the 7,000 and divided it by the length of the half-life, so 800 years. And that's the value then that I plugged in for T to get the amount of stuff left. So to do part C, I did that on my calculator, where I graphed this along with 1. And looked for the intersection. So I know that it's going to be longer than or less than 9 half-lives, right? Because it took a little, more than 9 half-lives is going to get me past 1 gram. So I'm just going to go 0 to 10, seems fine. The minimum I can have is 0 since it's decay, right? You can't get less than 0 grams of something. And we're starting at 50, so that looks good there. And I don't know, go by 5s, seems fine. That all looks good. Let's graph. So there's my exponential decay. There's my line for 1. So it intersected somewhere over here, it looks like. So second trace, pick the intersect command. And because there's only 2 curves in one intersection, I can just press enter 3 times. I don't really have to worry about moving anything around. So there's my 782 that I show here. But I have to remember that the value for T is in half-lives. If I want the answer in years, I have to convert it back. So that's why I multiplied by 800 years, because that's the length of 1 half-life. So if I have 7.8 half-lives, I multiply that by 800 to get the 6,259, whatever it is. Is that okay?
Yeah.
So I didn't do that one really live. I just kind of talked my way through it, because I think most of the work that you needed was on the key. So I just figured I'd explain where the things were coming from. Yeah, Pete?
If we go back to the graphing one, do we find horizontal or vertical as
So if it's exponential, the horizontal asymptote is y equals k.
okay, so it's okay.
There's no vertical. For a logarithmic, there's a vertical, and it's x equals h. There is no horizontal. That's it.
So it's just H for vertical and K for horizontal.
H for logs, which is vertical,
Yeah.
and k for exponentials, which is horizontal.
That's perfect.
Again, those are good things to go into your sheet, right?
Yeah.
So things to put on your sheet, I would put your properties of logs, right? I'd put your graphing stuff. I'd put the models on there. For sure, those things minimum, you know. Those will, probably the domain and range stuff, I'd consider that in with the graphing, right? Because there's little rules on how to do the domains and ranges. That's where I would start with my half sheet, is get all that stuff on there first, and then
Yeah, it's not bad.
worry about the other stuff. It's not that bad.
The graphing's pretty easy.
The graphing should be pretty easy. Very similar to what we've been doing.
It's just like this story model.
Okay. They're all, the nice thing about the story problems is like, once you get the setup, they're all kind of done the same way. It's just
there.
making sure you get it set up correctly is sometimes the tricky part. But after that, they're all of them are like the exact same questions, the exact same process.
Just a different code.
Yeah. So once you get it, you should be good.
Can you go over 17?
So the first thing I did was I condensed the two logarithms into a single log, because I need to have one log in order to cancel anything. So that's got me to here. And then to cancel out log base 3, I used exponent base 3. So that got rid of the log, so I'm left with just, when I multiplied the x through, I got x squared minus 6. And then on the other side, I have 3 to the third. 3 to the third is just 27. So if I subtract the 27 over to the other side, I have a quadratic equation that's equal to 0. Oops. I can then factor that, or use the quadratic formula. That would have been fine too. So multiplies to give me negative 27 and adds to give me negative 6 is negative 9 and positive 3. So my two potential solutions are 9 and negative 3.
Let's go back and check.
But if I go back and check, if I plug negative 3 in, it's going to give me a negative inside a logarithm, which is no bueno. So I got to throw that one out. The 9, though, I have 9 and then 3. That one should be good. Nope, not that bad. Not that bad. Should be doable.
Nice, but
Absolutely. Let's stop here. You guys can